Shall I give it one more minute? Tell me over there. I tried to write the short introduction, but it turned into a page and a half. Yeah, all positive. Yeah. All right. So welcome everybody to this week's school seminar. Before starting, we acknowledge and celebrate the first Australians on whose traditional lands we meet and pay our respects to their elders, past, present, and emerging. All right, I promise I won't get emotional. So, as you all know, today's seminar is a little different. It provides an opportunity for us to reflect on, and I'm not looking at Nerilie, and reflect on and celebrate the enormous contributions that Nerilie has made to RSES and the ANU. And the climate science community more broadly over the last 20 years or so. So Nerilie's academic journey began at the University of Sydney with a Bachelor of Science Advanced, and no surprises, she got first class honours and the University Medal. So some things never change. She completed a PhD here at the ANU in 2004. And then spent 7 years in the UK at the British Antarctic Survey in Cambridge, and then rejoined us at the ANU in 2011. And in the intervening years, has really developed a world-leading research program in paleoclimate science. There's a lot of big words in paleoclimate science, which are new to a geodynamicist, so I'm going to have to read some of this out. But Nerilie's research focuses on reconstructing climate variability over the past millennium, using corals, cave speleothems, that right? Did I get that right? Good. And Antarctic ice cores to reveal the long-term context for present-day climate change. Nerilie's made major contributions to our understanding of climate drivers, such as the Indian Ocean Dipole and the Southern Annular Mode, and how they relate to climate extreme events like drought and bushfire in Australia. Nerilie's ability to integrate climate records from across the tropics and polar regions has produced insights that are both regionally specific and globally relevant. Now, during her time at RSES, Nerilie's contributed to many major research programs and has played key leadership roles in the Australian Centre of Excellence for Antarctic Science, the ARC Centre of Excellence in 21st Century Weather, and many, many other things. Her group is supported both through the ARC, the Minderoo Foundation, and other sources, and this all enables important investigations into the long-term history of climate extremes and future risks in a warming world. Well, this is quite long. Nerilie's made outstanding contributions across academia, not only as a scientist, but as a science communicator, a policy advisor, and an advocate for evidence-based decision-making. Her insights have helped bridge the gap between research and policy, and she's become a trusted and effective voice in national and international climate conversations. There's only half a page on the back. Most recently, Nerilie was elected as a Fellow of the Australian Academy of Sciences, which I think we'd all agree is a fitting recognition of her excellence across research, leadership, communication, and public service. All right, this is where I get emotional. But whilst Nerilie's research speaks for itself, what's actually been very striking and has come through in the reflections that I've received from many of you within the room is the regard in which she's held as a colleague, a teacher, a mentor, and a leader. Now, I actually received way too many descriptions of Nerilie to read out, so I've had to try and summarize. So I've got this all in a paragraph. But there was actually, when I put these into a Word document, 6 pages of reflections came in on you, Nerilie. So this is distilled into 5 lines. Please bear with me. Across all the contributions, there's a strong and consistent message that Nerilie is not only an exceptional scientist. I know I'm funny, but but also an incredibly generous collaborator, someone who brings clarity, calm, and kindness to every role that she takes on. Her ability to make space for others, to mentor, to advise, and to help people grow has left a deep mark on many in this room. She's been described as inspiring, wise, inclusive, warm, tenacious, engaging, and genuinely kind. Her teaching has made complex ideas accessible and compelling for undergraduate students. Her leadership has helped steer major research bids, and her support has helped many colleagues, particularly women in science, to see what's possible and to believe in their place in this field. That was actually 8 lines. Sorry. Now, we're all very sad to see Nerilie leave ANU, but we're also very proud and very excited to see you take on the role of Chief Scientist at the AAD. It's a big win for the national research community, and frankly, I think we'd all agree a very wise choice. So that was the serious part. So Nerilie, thank you for everything you've done and contributed to RSES and to many of us personally, me included. You leave an extraordinary legacy, and whilst we're all hoping to see you around the place a lot through your honorary role, we're all genuinely excited about what the future will bring. So thanks for everything, and over to you.
Yeah, thank you very much for such a warm introduction. Okay, what I'm going to do today is to talk you through the 2 major projects that I've been working to wrap up over the last year or so. And so that's why this talk has a bit of a long title, because it is actually the merging of 2 distinct projects, but hopefully I can bring this together into like a narrative that makes sense as to how these seemingly very different areas are actually quite closely linked. So, get this going. Okay. So I'm going to start with looking at some of the evidence that we're seeing for abrupt changes in the Antarctic environment. This is a piece of work that I've been leading, and one of the really important parts, I think, with this work is that it's a project that has been able to bridge across all of the different Antarctic centres that we have in Australia and bring together the expertise to look at this really important problem. This is work that will be coming out in a few weeks' time in Nature. So the starting point is that we are in a world that's warming. So this is a statement of fact. It's unequivocal that the climate is warming because of the human influence. One of the things that we see as the climate warms is that the impacts of that in many cases have a direct relation to the magnitude of global warming. So these figures here from the IPCC are showing the expected change in rainfall at different levels of global warming. And what you can see across those maps is that the patterns are strikingly similar. They just get more intense the higher that warming level gets to. And that's where we can summarize this as every fraction of a degree of warming matters in terms of the impacts that we're going to face. But where we have something like this, where we can see this intensification with every fraction of a degree of warming, not all of the climate impacts that we are going to face are going to develop in this gradual way. And so we have this concept of abrupt change. And so abrupt changes are where we have changes in the Earth system that happen substantially faster than the normal rate of change in that part of the Earth system. So there's a few things to unpack with this. So firstly, when I use the term abrupt, abrupt in terms of a timescale depends on the type of system that we're looking at. So if we're thinking about the Antarctic system, we can have an ice shelf can collapse in a matter of days. That's abrupt. For sea ice, we can see sea ice loss occurring over timescales of months to years. That's abrupt for the sea ice system. But when we go to the ice sheet, abrupt changes are changes that are going to happen over decades to centuries. But importantly, even when we're talking about abrupt changes on those very long timescales, it's the emission choices that we're making now that are going to determine what we're setting in place in terms of locking in these abrupt changes and the magnitude of the abrupt changes. In terms of abrupt change, when a system undergoes an abrupt change, that can be described as a regime shift. So it's shifting from statistically one stable state to another. And a subset of regime shifts are tipping points. And so tipping points are where we have a large scale part of the Earth system that can, once we pass a critical threshold, rearrange abruptly and often irreversibly. There are many tipping elements that we know exist in the Earth system. And one of the striking things when you look at a map like this is that there's a real concentration of these known tipping elements in the Northern Hemisphere. And that doesn't mean that we don't have more tipping elements in the Southern Hemisphere. What it means is that we haven't had the evidence to be able to understand the potential risk of tipping points in Antarctica and the Southern Ocean to the same extent that we have information for the Northern Hemisphere. So I'm going to spend a bit of time talking about Antarctic sea ice. So Antarctic sea ice has been in the media and the scientific eye particularly keenly over the last few years because of this really precipitous decline that we've seen in Antarctic sea ice since 2014. So prior to 2014, Antarctic sea ice was actually showing a small increase in sea ice extent. It was one of these climate change paradoxes. We're in a warming world, but why was Antarctic sea ice increasing? But after 2014, we've had this really rapid decline in Antarctic sea ice. And in July of 2023, if you were to put a statistical number on that, the extent of that anomaly was a -7 standard deviation event. So really highly unusual in terms of the statistics of how we understand this system from the satellite record of Antarctic sea ice. And again, just to put that in context as to just how much sea ice we're talking about, on this map for July 2023, everything that's shaded red is where there wasn't sea ice, when normally we would have expected there to be sea ice. And if you add up all of those red areas together, that's the size of Western Australia. So a huge amount of area that is no longer being covered by sea ice. So this has been described as a regime shift in Antarctic sea ice, but with the caveat of, well, just how much do we understand this as a regime shift based on the observational record that we have? So we only have the satellite observations of Antarctic sea ice since 1979. Is that enough for us to really understand if this is a regime shift compared to natural variability? And so this is where we can start to pull in other evidence that we have for what Antarctic sea ice was doing before satellite observations. I'm just going to show one reconstruction here. This is the reconstruction by Ryan Fogt in orange. This is based on a reconstruction of sea ice from historical observations of temperature and pressure and climate indices. And what you can see in this reconstruction is that natural variability, a long-term 20th century decline before we had this slightly unusual period of sea ice increasing in the early 2000s, and then the very precipitous decline since 2014. So I'm just showing one reconstruction here, but we can do this same analysis for a whole range of reconstructions, and they all show this same picture that really puts it into perspective that what we've seen happening in Antarctic sea ice over the past decade is really very unusual and not part of the natural variability of this system. The other thing that we can see when we look at all of these reconstructions is that if we look at the 20th century as a whole, Antarctic sea ice was actually declining. There was a statistically significant declining trend in Antarctic sea ice, but this wasn't evident in our satellite observations starting in 1979 when we had this warming, this period of increasing sea ice in the early 2000s. If we were to continue to extrapolate that 20th century trend, the drop that we saw in Antarctic sea ice in 2016 could be considered as just a continuation of that long-term 20th century trend. But the drop that we had in 2023 seems to far exceed what we would expect from just a continuation of that long-term declining trend. So evidence of, again, an abrupt change and perhaps an intensification of Antarctic sea ice loss. So one of the things that we can ask is, how does the Arctic sea ice decline compare to what we're seeing in Antarctica? So if we look at the sea ice maximum, so that happens in September in Antarctica, it happens in March in the Arctic. We can see this long-term decline in Arctic sea ice maximum over the length of the satellite record. For the Antarctic, we see that precipitous decline over the last decade. The speed at which Antarctica has lost sea ice over the last decade is more than 4 times faster than that long-term decline in the Arctic. So what that means in effect is that the amount of sea ice that's been lost from around Antarctica in the last decade is of the same magnitude as the total loss of sea ice in the Arctic over the last 46 years. If we look at the summer sea ice minimum, one of the things that's often discussed is, when will the Arctic become ice-free in summer? And the most recent IPCC assessment was that that's likely to happen at least once before 2050. So that's when that blue line will come down to having at least once hitting these ice-free conditions. So that's described as a sea ice extent that's less than 1 million square kilometres. If we compare that to the Antarctic, we see again that the decline in Antarctic summer sea ice over the last decade has been faster than the long-term decline in the Arctic summer sea ice. But we also are starting from a lower level of sea ice. So the Antarctic has less sea ice coverage in the summer compared to the Arctic. So if that trend were to continue, it is possible that we would see ice-free summers in the Antarctic sooner than the Arctic. And then the final comparison here, one of the consequences of the long-term decline in Arctic sea ice has been the amplification of climate warming over the high northern hemisphere. And that's because we're taking a reflective white surface and we're replacing it with a darker ocean surface, which is able to absorb more energy. And so we can describe that as the radiative forcing or the radiative effect of sea ice. So again, in the blue line, we see that gradual increase in the radiative effect over the northern hemisphere. But the changes that we've seen in the Antarctic in purple over the last decade mean that that radiative effect that we're seeing in the southern hemisphere is now of an equivalent magnitude to what's been experienced in the Arctic. And so we could expect from this to see an amplification of climate warming in our region moving forward. So on that tipping points map that I showed earlier, when you see maps like that, often they refer to Arctic sea ice as being a potential tipping element. But the most recent assessments is that the Arctic sea ice doesn't actually meet the definition of being a tipping element. And the reason for that is that the Arctic sea ice shows a very linear response to climate warming. And so what these experiments are showing, these are very long climate simulations that are run under net zero scenarios. So the top panel is showing the temperature evolution. And so what these experiments do is they take our emissions trajectory and say from 2030, they cut off all emissions and then just let that model run and see what happens in that zero emissions scenario. And they do that every 5 years, so up to continuing to emit up to 2060 and then zero emissions from then on. And so you can see it, the global temperature, as soon as you stop emitting, your global temperature stabilizes with a small sort of continuing increase, but it stabilizes relatively quickly once you move into that zero emissions scenario. The two panels on the left below in blue colors are showing the response of Arctic sea ice. So again, you can see as soon as you stabilize the temperature, you also level out your Arctic sea ice. And that's plotted on the right-hand side where we're showing global temperature versus sea ice response. And you can see this very linear relationship where the amount of sea ice that we lose from the Arctic depends linearly on how warm the climate gets. And once we stabilize climate, we stop losing Arctic sea ice. And now the reason that I've spent so much time explaining that is because when we look at those same experiments and we see what happens with Antarctic sea ice, we get a very different picture. So in the Antarctic, even once we reach a net zero scenario and we stabilize global climate, we continue to lose Antarctic sea ice. And this is because of the additional heat in the Southern Ocean. But what you can see, particularly focusing in on the bottom panels, is that even once we stabilize temperature, we continue to lose that ice. And so this has much more of an indication of Antarctic sea ice being a tipping element than what we see in that same comparison for the Arctic. Right, so that's the summary of where we're at in terms of Antarctic sea ice. But we're seeing abrupt changes in a number of other parts of the Antarctic environment. And the Antarctic environment is very interconnected across what's happening in the ice, what's happening in the ocean, the solid earth conditions, and the biological systems that depend on the ice and the ocean and the land. So, for example, the deep water ocean circulation is a very fundamental part of Earth's climate system, made quite famous through movies like The Day After Tomorrow. What happens if you shut down that deep ocean circulation in the North Atlantic? Well, the Antarctic has its own equivalent of that same process, where we form very dense cold waters around the coast of Antarctica that then flow down to the bottom of the ocean and out around the world. Again, a really important part of Earth's climate system. So the places where dense water forms around Antarctica is quite close to the coast in these orange areas here. And so this is what we're now seeing from observations and climate model simulations. So in the panel on the right-hand side here, the black line is showing our multi-model CMIP type climate simulations of what happens to the Antarctic overturning circulation in a warming climate. And so we can see that those climate models are projecting that we will, as the climate warms, continue to see a slowdown of that Antarctic overturning circulation. In purple climate model simulations, where we're using models that are able to accurately reproduce the process by which we form this dense water around the Antarctic continent. And these are simulations where we also add in meltwater around the edge of Antarctica from the loss of continental ice and melting of ice shelves. And we can see that when we add in that meltwater, that we see a much stronger response in terms of how quickly we might expect the Antarctic overturning circulation to slow down. And so that's a 40% decline by 2050 in those projections. And then in blue and green are observations from areas where this overturning circulation starts. And in those two areas, we've actually already observed a 30% decline or 30% slowdown in Antarctic overturning circulation. So evidence that we're seeing a dramatic change here, and that from observations, we may actually be seeing that playing out faster than we expect from climate simulations. When we look to West Antarctica, even under the best case emission reduction scenarios, we are expecting that we could trigger the tipping point in West Antarctica, and that would result in 3 meters of sea level rise, equivalent globally. And in terms of trying to improve our predictability of that, what we can do is to look at, in blue, where are we observing changes in the ice sheet? And in purple, where do we think that the ice sheet is most susceptible based on what we understand about where is there water beneath the ice sheet, what's the geology like of the ice, and those things that make the ice sheet potentially susceptible to this rapid tipping point behavior. And if we combine those susceptibilities with the observed changes, we have a way of producing this map of potential vulnerability and highlighting really the areas of concern where scientifically we would want to put our efforts into understanding the potential risks and improving predictability. In terms of biological systems, in the terrestrial and marine systems, we are seeing regime shifts playing out around Antarctica. We're seeing an expansion of plant life on the Antarctic Peninsula as ice is lost and there's more habitat becomes available. We're seeing changes in the seafloor assemblages, particularly where sea ice is being lost and ice shelves have collapsed, and that changes the light availability for these seafloor communities. And then we have sea ice being an important habitat for things like krill. One of the really concerning developments over the last decade has been the impact on emperor penguin colonies from the loss of Antarctic sea ice, and particularly the fast ice around the edge of Antarctica, which is a critical breeding habitat. And so when that fast ice breaks out earlier than usual, and the penguin chicks haven't fledged to get their waterproof feathers, in those instances we see complete breeding failure of the colonies. And what we can see around Antarctica is that these events where we have these catastrophic breeding failures are happening right around the continent, and we're seeing some colonies that have been affected multiple times over the last decade. So a risk that is compounding both in time and in space, and has the potential to increase extinction risk. Right, so how do we bring all of this together? So if we look at the Antarctic system, we've got multiple climate pressures that are affecting the system and driving abrupt changes in the Antarctic system. And so this is climate warming, increasing ocean heat, sea level rise, changing weather patterns, and ocean acidification. But we also have interactions between the changes playing out in the Antarctic. So for example, when we slow down Antarctic overturning circulation by reducing the amount of dense shelf water being formed around Antarctica, that brings more ocean heat up onto the continental shelf and into these ice shelf cavities, and increases the melting of those ice shelves in the front of the ice sheet. And at the same time, that melting of the ice shelves and the ice sheet increases the meltwater that's being put into the ocean, which inhibits that dense water formation. And we can find a number of these areas where the changes that we're seeing in one part of the Antarctic system have the potential to amplify the impacts on other parts of the Antarctic system as well. Oh, I missed a slide there, sorry. There was also meant to be a slide there showing upward arrows where each of these changes in the Antarctic system also feed back with amplifying feedbacks back up onto global climate change. In terms of how we use this information, we can use this to identify areas of concern. This is particularly Australia focused. So for Australia's Antarctic territory and the 42% claim that Australia holds, we can see areas where in dark blue, areas of the ice sheet that are areas of concern for the dense water production regions, and the penguin icons showing areas where we've seen these colony scale breeding failures for emperor penguin colonies. So what can we do about it? The policy responses, particularly through the Antarctic Treaty System, generally have been focused on this biological side, so things like reducing non-climatic pressures and establishing protected areas. So those are really important things to pursue for building resilience in that part of the Antarctic system, but they don't do anything to stop the downward pressure that we're seeing from these multiple climate change pressures. So that brings us to deep and rapid carbon dioxide emission reductions is the only thing that's actually will be effective for reducing that external climate pressure on the Antarctic, but that is going to have to be combined with adaptation planning that considers the plausible futures where we have further abrupt changes in the Antarctic environment. And so that's my segue into the next part. So we've got these abrupt changes in the Antarctic system. The only way to effectively reduce the risk of those worsening and new abrupt changes developing is by reducing carbon dioxide emissions. So the other project that I've been working on, and this is including with funding from the Minderoo Foundation, is to look at how we can bring scientific evidence into decision making around our emissions, and particularly related to fossil fuel projects. So we've got a global problem in terms of climate change, and this is to do with cumulatively the global emissions that we make of carbon dioxide into the atmosphere. We have the Paris Agreement, which is a global agreement that says that we should limit warming to well below 2 degrees above pre-industrial levels and pursue efforts to limit warming to 1.5 degrees. So that's where we are for a global problem. We then have the actions that are taken at national levels and the commitments that are made through nationally determined contributions as to how different countries are going to reduce their emissions. So Australia's nationally determined contribution is currently that we'll reduce emissions by 43% by 2030 and reach net zero emissions by 2050. So that's where we are. So at a national scale, we have this national scale commitment as to what we're going to do to reduce emissions, to play our part in solving this global problem. But the decisions that are made in terms of future fossil fuel projects are made at an individual project level. And so we've got a global problem, we have a national commitment, but the decisions are made at this much smaller scale for individual projects. When these project proposals are put together, there are guidelines for how they should report their anticipated greenhouse gas emissions. And so there's a very sort of standard way that that is done. But there aren't similar standards for what they then do with those anticipated emissions in terms of describing what their climate change impacts are going to be. And so by going through and looking at a number of these project proposals, we can identify a few pervasive issues. And by pervasive issues, I'm referring to areas where when we look at these project proposals, the information that's being presented by proponents is inconsistent with our climate science understanding. And so to summarize these areas, the first is what's the contribution of the project to global warming? How acceptable are the climate change impacts that will result from that contribution to global warming? And what are the contexts? What's the context that those emissions are being made under, and particularly in relation to nationally determined contributions? So to walk through sort of an example of how we could bring scientific information into this area, I'm going to run through a case study demonstration. So this is a case study, but what's being shown can be applied in the same way to any fossil fuel project. But for this case study, which is based on the Scarborough project, so an offshore gas project in Western Australia, the project proposal estimates 31 years of gas production. That's estimated to start in 2026. The total emissions from that project are anticipated to be 876 million tonnes of carbon dioxide. That's the emissions both from producing and processing the gas and the consumption of that gas. Of that 876 million tonnes of carbon dioxide, 192 million tonnes fall under Australia's jurisdiction in terms of carbon reporting. So that's the production and the processing emissions, and then the consumption of the gas that's anticipated within Australia. So for this project, there's a 15% requirement by the West Australian government for gas to be used within Australia. So some of the statements that you can pull out of this project proposal, in terms of their climate change contribution, the statement is that it's not possible to link greenhouse gas emissions from this project with climate change or any particular climate-related impact, because it's the net global emissions or concentrations is written here that cause climate change and climate-related impacts. And the estimated emissions from this project are negligible in the context of future global greenhouse gas concentrations. So we're so small, we're negligible, so you can't really quantify what the impact is. So because that impact on global warming isn't quantified, the risk assessment for the consequences of that warming is also not undertaken, and it's assumed that the impact of the greenhouse gas emissions from the Scarborough project will be negligible for all receptors. Right, so the starting point for bringing scientific evidence into here, we can look to the most recent IPCC assessment. We have this statement that every tonne of carbon dioxide emissions adds to global warming. This is quite a powerful statement, particularly being in the summary for policymakers of this document of the IPCC report. This reflects that it's been approved by consensus as of all of the 195 member governments of the IPCC as an accurate reflection of the underlying scientific evidence. So every tonne of carbon dioxide emissions adds to global warming. And we can see this nice linear relationship between cumulative global emissions running along the x-axis and the amount of global warming that is caused. And so this linear relationship means it doesn't actually matter how quickly or how slowly we emit carbon dioxide. It's the total amount of carbon dioxide that we emit that will determine how much global warming the world faces. So the first thing just to highlight is this perception issue. So we talk about carbon dioxide emissions in terms of millions of tonnes or billions of tonnes of carbon dioxide emissions. And when we do that, the numbers sound quite small. So 876 million tonnes of carbon dioxide, it's only 876, but it's 876 million tonnes of carbon dioxide when we know that every tonne of carbon dioxide matters. So just to point out, I think that just the way that we talk about these emissions makes us think that the numbers are small when they're not. The way that we quantify the amount of warming that will be caused by those emissions is through a relationship known as the transient climate response to carbon dioxide emissions. This is a really powerful relationship because it's a very simple relationship and it directly links the primary cause of climate change, so global emissions of carbon dioxide, with the primary measure of climate change, so the warming of Earth's climate. This is what that relationship is. So for every 1,000 billion tonnes of carbon dioxide emissions, we expect that to cause 0.45 degrees of global warming. And there's a likelihood range on this as well. And just to point out that in what I'll show going forward, we continue to propagate errors with every step of the calculation. We combine the errors that we are bringing in to make sure that we're giving a best estimate as well as a likely range as well. So if we go back to our case study, we've got this 876 million tonnes of carbon dioxide emissions that we expect from this one fossil fuel project. Through the transient climate response to emissions, we can quantify that this project would be expected to cause additional global warming of 0.00039 degrees Celsius and a likely range. So a very small number, a number that is too small for us to be able to measure that amount of climate change, but a number that is knowable. And because we have quantified that, we're then in a position to be able to quantify, well, what are the impacts of that amount of additional global warming? So a very small number, but a number that is still meaningful. So by quantifying that additional warming, we can then move on to doing an assessment of quantified consequences. So I'm just going to run through 3 examples of the types of consequences that we can quantify. There's something called the human climate niche, which is a well-established relationship between population and mean annual temperature. And this human climate niche are the conditions that sustain human life and activity. This is what the human climate niche looks like. So this on the left is showing population density across the world compared to mean annual temperature. And then on the right is what this relationship looks like as we have different levels of global warming. And so as the climate becomes warmer, we start moving more and more people out across beyond the hot end of the human climate niche, so into a local climate where the mean annual temperature is 29 degrees or higher. And we change the distribution of the mean annual of the where people are sat relative to the climate niche. And so we can look at the relationship between global warming and the fraction of global population who are either exposed to unprecedented temperature. So that's their local climate has moved above the hot end of the human climate niche, or looking at the full distribution of the human climate niche, what proportion of the population has been moved outside of the human climate niche when we take into account the full distribution. So these are the 2 things that are shown here. You see these linear relationships between the fraction of the global population that's affected and the global warming level. And so what does this mean in terms of a world with 9.5 billion people, which is what's estimated by the middle of this century under a middle of the road type scenario for the future? And this is where we see that our small number actually has a meaningful consequence, so that 0.00039 degrees of additional global warming is expected to result in an additional 500,000 people who are exposed to unprecedented heat, an additional 356,000 people who are left outside of the human climate niche. So one of the consequences of moving people outside of the human climate niche is an increase in climate-related mortality. One of the areas in the world where we have information to be able to quantify this relationship is Europe. So this is data that's been developed using health information from across 854 cities within Europe. And again, what we can see are at different levels of global warming. What does this mean in terms of changes in the excess death rate? And purple colours are where you have an increase in the excess death rate. Green colours are where you have a decrease in the excess death rate. And so generally, southern areas, as it gets hotter, you increase the death rate across Europe. So again, we have a relationship where we have global warming, and we can look at how that change in global warming level relates to cumulative deaths in Europe up to the end of the century. And the quantification here is that that small amount of additional warming from this one fossil fuel project would contribute an additional 484 heat-related deaths in Europe by 2100. And then the last example is what does this mean also for natural systems and the consequences for them. The Great Barrier Reef is an example of an environment that's already experiencing the damaging effects of climate warming. And so what we can do is to look at degree heating weeks. So this is the thermal exposure that is used to look at the risk of coral bleaching. How does that thermal exposure change on the Great Barrier Reef as global mean surface temperature changes? And then what's the relationship of that change in thermal exposure to the amount of coral cover that's lost? And when we run through that quantification, we can see that that additional global warming will cause an additional 0.0017 degrees Celsius weeks in accumulated heat exposure across the Great Barrier Reef Marine Park. And what that means is that for every future bleaching event, you would expect an additional 16 million corals to be lost across the 1 million hectares of reef environment within the Great Barrier Reef Marine Park. Right, so there's 3 examples of consequences that we can quantify, having been able to first quantify the additional warming related to an individual fossil fuel project. So if we come back to the risk assessment that was done in this project proposal, where the impact was evaluated as negligible for all receptors, in the risk assessment framework within that proposal document, negligible refers to consequences for the environment or social and cultural consequences that have no lasting effect. They last for less than a month. They only have localized impact. So that's not a great description for those 3 examples that I've just shown. So again, these 3 examples, just a few illustrative examples. So if we think about actually sort of what does this mean in terms of how severe and persistent those impacts are, the best description of that would be that this is a level A or B, so a catastrophic to major consequence for those examples. The other thing I mentioned is that we propagate the uncertainty all the way through, so those consequences have been quantified to be in that likely to highly likely range, which allows us to then take the consequence and the likelihood and map that into a risk assessment. And so our risk assessment under those settings comes out as severe, which would mean in a normal situation that you would then be looking at what are the additional factors that we can put in place to bring that risk down to an acceptable level. Right, so the final thing I just wanted to touch on was the emissions context. And so, and again, another couple of statements from the project proposal document. The key thing here being that when we look at across a number of these project proposal documents, they will describe the context of their emissions, so their contribution to a state, a national, a global level relative to a fixed point in time. In this example, it's relative to projected emissions in 2030. And often the quantification is given to a time in the past. So how do these emissions compare to 2020 emission levels? And so that using a fixed point is a bit of a problem when we're in a period of time where a project is extending across the same period of time where we have a nationally determined contribution for making rapid and deep emission reductions. So again, if we return to this figure here, we know that the amount of warming that we'll face depends on our cumulative emissions. And that leads us to be able to say that if we want to limit warming to 1.5, we know what our total emissions are. We know what we've already emitted, so we know what's left. What's our budget left if we're going to limit warming to 1.5 degrees? Globally, this is what our remaining carbon budget now looks like for limiting warming to 1.5 degrees. So that is, I would say, no longer feasible. This is what the global budget looks like for limiting warming to 1.7 degrees. So that would fit the description of well below 2 degrees. Still an absolutely enormous challenge to not only level off emissions, but do that downward trajectory to net zero emissions. But that's what globally it looks like as at the start of 2025 for what our remaining carbon budget is to limit warming to 1.7 degrees. In terms of that global budget, we can then ask, well, what's Australia's fair share of that? There are a number of different considerations that go into a fair share. The Australian government has previously said that 0.97% of the global budget would be one way that we could consider our fair share. And so using that value, this is what Australia's remaining carbon budget looks like for limiting warming to 1.7 degrees. And then purple shows the plot of what our nationally determined contribution would look like. So our nationally determined contribution, if we could achieve that, would be roughly equivalent to doing our fair share of limiting warming to 1.7 degrees. And then we can put the context of a project into that. And so At the start of this project in 2026, the anticipated Australian emissions, so only the Australian consumption and then the production and processing emissions, would amount to about 1.8% of Australia's total carbon budget for 2026 under that emission reduction pathway. By 2030, we're up to 2.5% from this one project. By 2040, we're up to 5% from this one project. And at 2049, it's half of Australia's remaining carbon budget for that year. And then all emissions beyond 2050 are in this period of time where Australia has pledged to have reached net zero. So all of those emissions exceed our budget. So I just wanted to just highlight this decision that came out from the International Court of Justice just last week. So a really powerful decision that came out as this advisory opinion. And one of the features within this advisory opinion is that countries do need to use scientific evidence in considering their climate change impacts. And so hopefully what I've shown you is a way that we could bring that scientific evidence in a practical, forward-looking way to help aid decision-making when we're considering these future fossil fuel projects by looking at what their contribution to global warming is, the acceptability of those climate change impacts, and then the context of those emissions as well. And so a final slide just to say thank you to everybody. Now I'm going to try not to cry. But yeah, huge and heartfelt thank you to everybody who has made my time here so enjoyable, being able to do the science that I love with great people. I'd also extend that shout out to the allies that I found at RSES at the times when things weren't okay. There were people here who stood up beside me, and I hope that we've made academia a better place because of that. And so, yeah, thank you to everybody. I am really sad to be leaving you, but I'm excited about the next journey and looking forward to continuing to interact with you in my new role. So thank you very much.
Thanks, Nerilie. That was amazing. So do we have any questions? We also have 60 people online now as well. So online people, if you can probably put your hand up and you should be able to speak when we come around to you if you'd like, or you can also put questions in the chat as you prefer. So we might start with questions here first. Yes.
Hi, thanks for the talk. It's fantastic. My question, I mean, we have the results now that, you know, looks like Scarborough projects are likely to kill something like 500 Europeans. How do you then use this data to then take to the courts and say, look, you've lied, one, in legislate in a report, but two, this is the real impact, and how do you then like put that into something that we can use to then get back?
Yeah, well,
just repeat for the online.
Yeah. So I guess a summary of Oliver's question was how do we use this information? How do we actually take this information? So I think ideally you would actually have regulations put in place that when these fossil fuel project proposals are put together, they actually have guidelines as to how you bring into and take into account these climate change impacts. I don't anticipate that would be a fast thing to happen, but ideally I think that's where it would go. I think in the meantime that climate litigation probably does have an important role to play in terms of putting sort of the pressure on as to actually making sure that we are bringing that scientific evidence into how we're thinking about these decisions, and just bringing it back into making sure that we're not sort of just saying this is too small to count, this is too small to count, that actually it's everything together and that actually we're at a point where every single decision matters. So I think that ideally we would have a regulation as to sort of how we bring this information in. In terms of what we're doing to move that project forward, we've got a research associate who actually started with us under the Minzuru project last week. And so she's going to be looking both at ways that we bring more examples into this so that we can have examples that are tailored to or relevant for the different ways that people might want to be looking at this methodology, but also putting that the code that we've got into an interactive interface so that it's available for people to be able to easily be able to utilize the method without actually being able to go in and dig into the coding as well.
Yes.
Thanks, Nerilie, that was great, and I really love the way you sort of translate that into sort of real world impacts from what seems like a small number. And just along those lines of other ways you can express that sort of impact is that I'm sure you're aware of this, there's the thing called the social cost of carbon, which effectively tries to produce a net economic effect of emitting a ton of carbon. So there was a review a few years ago which gave a number of $417 per ton. That translates to about $500 billion for Scarborough on your basis. And if you look at the proponents' assessment of benefit nationally, it's 50 billion, assuming you actually pay any tax at all, those taxes and royalties. And so effectively Australia says it's okay for us to score $50 billion of taxes, but we're happy to make the world pay 500.
Yeah. Yeah, so I guess repeating that was from Mark Haddon, and so pointing out that other work that's going on for quantifying the cost of carbon, so an economic cost, and how do you weigh that up between the cost versus the benefit of that carbon. Yes, I think that social cost is a really important thing. I think one of the approaches that we took in this project was to also try and develop these examples in a way that's tangible, that people will be able to relate to. And I think sometimes that social cost or the economic cost of carbon, you end up with a number that's really big and should be meaningful, but it's hard to actually relate to. And so that was part of this, trying to actually get to these sort of tangible examples as to, is this a better way to try and sort of communicate that? But I think absolutely how do the costs of these projects compare to the benefits of the projects is really important. And even sort of if we think about that emissions context, we have, as when we approve these projects that go beyond net zero, we're implying that all of those emissions are going to be removed from the atmosphere somehow without factoring in the cost of that. So I think that's the other thing that hopefully this methodology just helps to crystallize some of those things that we should be thinking about in terms of the life cycle of these projects.
Any other questions? Do we have any questions? Oh yeah, Zana, do you want to try unmuting and speaking, Zana?
Yeah, hi Nerilie, that was an amazing talk. Thank you so much. I love the idea of quantifying the actual impact of the emissions, but I am curious it seems like such an obvious misuse of the risk assessment in the first place. What's your assessment of why that wasn't picked up by whoever it was that was reviewing this risk assessment?
Well, I would say that it's consistent across. So I've shown one example from that project, but all of those project proposals have risk assessments, and all of them reach that same type of conclusion in the same way by not quantifying anything. And so the assumption that this is a global problem, we're so small that we can't possibly actually matter. And so yes, I've demonstrated it as a project, as a problem with how it had been applied in the Scarborough project, but across all those other proposal documents that we looked at, you see that it's a common way that the information is presented by the fossil fuel proponents in these project proposals.
Yeah, but I guess it seems like such a flawed reasoning. It does sort of suggest that it's not that there's a problem in the way that they're being assessed, that would kind of pass and not be critically questioned at any point. I guess it's not surprising in a way, but it does suggest that there's another problem.
Yeah, I agree, and I'm hoping that the publication that we have coming out on this is a step forward in helping to provide a way of being able to bring that scientific basis into that decision making.
Yeah, great. Thank you.
Thanks, Anna.
Okay, we might do, yeah, we've got one more question online from Carl Bennett and Nicola, so we'll do those two last questions. Do you want to go first?
I'll try and make this a quick one, Nerilie. Thank you so much for your talk. I'm just wondering if you're potentially linking up with people who are reviewing the EPBC Act that Labor will probably be looking at in this term of government to start to get your climate risk accounting methodology into the Act.
So we haven't linked up with people working on that, but that's exactly the reason why the Great Barrier Reef quantification is done, because under the EPBC Act, there are matters of national environmental significance. That's something that should be addressed in these project proposals, and you do see it mentioned. But again, with in the project proposals, it says that they're not going to have a meaningful impact on matters of national environmental significance. And so the Great Barrier Reef is one of the things within the EPBC Act, and so that's why we did that quantification. And the research associate that we've got working on this project will be looking at the other examples that we might be able to help develop that fall under the EPBC Act as well.
Great. Nicola?
Yeah, great talk. Thanks. I guess I have a question about the first part of the Antarctic sea ice, and you've shown that it's a tipping element, basically. Have you considered whether there's a pathway that could make it come back? That kind of makes sense. And if so, how non-linear that is, and whether there's a way we could, if we hit this kind of tipping element, we would ever come back to where we are now.
Yeah, that's a good question. So the question from Nicola was about Antarctic sea ice and the evidence that seems to be developing that Antarctic sea ice is a tipping point. And is there a scenario where you can recover and bring sea ice back, and on what timescale would that happen? I haven't looked at that. I'm not aware of studies that have looked at that. The caveat in what I showed there is that that's one climate model simulation. So that's the net zero scenarios that have been done with access. So I think this is something to be tested more thoroughly across different climate models. One of the issues that we have in terms of climate models and sea ice is that even up until sort of the most recent IPCC report, we've said that we've got low confidence in our ability to simulate sea ice. And that's largely because the observations of that increase in Antarctic sea ice were completely at odds with climate model simulations, which all said Antarctic sea ice should be declining. What's going on? And so I think that that's something to do that re-evaluation, including bringing in some of this pre-observational information to get a better idea as to where our model's actually doing okay in terms of sea ice. What can we trust? Where are we still sort of concerned? And then going on and developing those other experiments as to how much of this is looking like it's a tipping element, and over what timescales is that irreversible or not? Yeah.
Great. There are a few more questions online, but we're going to leave it there. Sorry, online people, but if you could send your questions to Nerilie, because we have a lot of cake that needs eating. And we also have Kieran waiting for us as well. So I suggest everyone will head out and get cake and tea and coffee, and then come back in and sit around here. We might have a few more words for Nerilie. Let's thank Nerilie again for that amazing.